Current crowd simulation algorithms work well on 2D surfaces and surfaces that are approximated by a series of 2D planes. Our work extends crowd simulation to work on surfaces of any topology. With our algorithms, crowds can move on any surface, such as multi-story buildings. In addition to natural formations such as caves and arches, extraterrestrial environments such as asteroids and spaceships, and surfaces where insects swarm. Path planning is difficult on arbitrary surfaces, since it is hard to build navigation meshes without adding distortion. It is difficult to move agents around tight corners and edges, and surfaces can have huge triangle counts. We resolve these issues by improving discrete geodesics with away from edges, corridors, and line of sight algorithms. Obstacle avoidance is also difficult, since surfaces can have collision false positives, false negatives, and struggle with the non-spherical nature of agents. We resolve these obstacle avoidance artifacts by improving a Euclidean distance approach with an approximate vision algorithm and account for the non-spherical nature of agents. Our goal is to create the same natural crowd movement seen in traditional 2D algorithms like this one. Shown here are results of our algorithm in a multi-story building. Our path planning improvements move agents naturally around tight corners and stairways. Without our improvements, discrete geodesic algorithms would lead to immediate jamming. Our line of sight, away from edges, and corners optimizations remove this jamming. Empirically, our optimizations reduce stalling by 2 orders of magnitude over standard discrete geodesic methods. Visually, agents move smoothly around the corners of the stairs and form natural lanes. What makes our work unique is the range of surfaces on which it works. Examples of more complex surfaces include this globe. Since we do not flatten surfaces to do path planning, our crowds create natural curling patterns, such as the one seen here. Note that these agents group and then unwind at the pole of the sphere, where the triangles are the smallest and the math is the most difficult. Note that we use the same algorithm on this globe as we did on the multi-story building. Ants on this thin board highlight the power of our obstacle avoidance algorithm. Without our approximate vision algorithm, the ants move unnaturally, since they are trying to avoid ants on the other side of the board. This is emphasized when the board is transparent. With our optimizations, the ants do not try and avoid collisions with the relevant agents, and the motion is far more natural. Similar results are shown here in this multi-story building. Without our obstacle avoidance improvements, the agents on different floors try to avoid each other, something that wouldn't happen in real life. With our approximate synthetic vision algorithm, the agents correctly ignore each other. A similar scenario is shown on the science fiction surface. Without our approach, agents on the floor would walk through agents on the ceiling since their surface distance is high. With our optimizations, the agents avoid each other and do not collide. Results on other surfaces include the Stanford bunny, shown here. Note that our approach works well on both highly curved surfaces, like this bunny, and multi-story structures without changing parameters. We believe we are the only algorithm that is flexible enough to run on both types of surfaces. This ant infestation in a room highlights our algorithm's ability to move agents naturally even around perpendicular walls, floors, and ceilings. Our agents move smoothly around this Moebius strip. Without our optimizations and algorithmic improvements, agents would jam frequently and stall when their destination is on the other side of the Moebius strip. Notice that agents are close to the agents on the other side of the strip, but they are not false positives and false negatives. Additionally, agents do not jam or stall if their destination is on the opposite side. This soccer ball with the pentagons removed features both sharp turns and a highly curved surface. Again, without our optimizations, agents would jam and stall frequently. With our optimizations, the agents move naturally. This mesh features both the interior and exterior of a building. Without our improvements, agents form unnatural lines along mesh boundaries and jam around corners. With our improvements, the agents flow naturally, both inside and outside the building. Results show that our algorithm is complete, since discrete geodesic algorithms always find a path if one exists. Our results are fast. All our surfaces averaged at least 40 frames per second, even with surfaces of over 100,000 triangles. And our path planning improvements can actually result in a net increase in frames per second. Empirically, our improvements bring stalling to practically zero in our trials. We also show empirically that our improvements keep our path performance high. Qualitatively, our agents show key global features such as handling sharp corners, forming lanes, and forming curls. We also empirically show that our algorithm is correct, by showing that median collision rates across our tests are practically zero. Thank you for your attention.